Hello everyone, in this lecture of Dynamics of the Lithosphere we will discuss about composite creep laws. This is the third part of the lectures on viscous creep. So, why do we need a composite creep law? In fact, when the rocks deform, different deformation mechanisms can occur. And last week we briefly discussed about dislocation creep. Remember this picture of dislocations in a quartz grain. And we've discussed about diffusion creep. Remember, with the diffusion of vacancies going through the mass of the crystal. How can we account for both effects? We've seen equations to characterize both of these mechanisms, but we don't know how to make a model that can account for both end members. So, when we want to account for both end members, we will talk about dominant deformation mechanisms. So, in one regime, diffusion may dominate over dislocation and vice versa. To model this behavior, we will use the principle of additive strain rate decomposition. What does it mean? It means we employ Maxwell's model. And the Maxwell model is stated as such. The strain rate is a sum of individual contributions from the different deformation mechanisms. So here we have a sum of n deformation mechanisms, and each of these deformation mechanisms have or take a part of the total strain rate. So if you want, this would be a total strain rate, and this would be the strain rate of each of the deformation mechanisms. So what is important to know about this model is that deformation mechanisms have different strain rates, but each of these elements, the diffusion creep element, the dislocation creep element, and so on, they all feel the same macroscopic stress. So we have different strain rates, but same stress. So let's make an example. Now, if we would combine diffusion and dislocation creep, we would write up the total strain rate as being the sum of a diffusion creep strain rate and a dislocation creep strain rate. And each of these elements are feeling the same stress. So a useful representation of this is called the deformation map. So you have an example of a deformation map here. You have the shear stress in log units and the temperature on that axis. And what you can construct, you can, for example, plot isocontours of strain rate, and you can see the boundary between different fields. So this line here shows you the boundary between diffusion creep dominant deformation and on that side dislocation creep dominant deformation. So you can plot this type of diagrams. For this you need to make an assumption, for example a Maxwell model. Other deformation mechanisms may occur. So here you would have a high temperature or low stress creep, and here a high stress deformation mechanism, the brittle failure, which we will discuss in a couple of lectures. So this map, we will construct a boundary between diffusion creep and dislocation creep in the exercise 1 of this lecture. Another important point that we should keep in mind is that we've been discussing the lithosphere previously as being an elastic medium. Remember, from this seismology, we know that the internal structure of the Earth, because seismic waves are traveling through the Earth and they arise from elastodynamics. So we know that on the time scale of wave propagation, the Earth is elastic in a large regions. But we also know that plates are flexuring with, and this can be modeled with an elastic model. So the plates are indeed elastic. The lithosphere should be elastic So we want to construct a model that combines both viscous creep and elastic deformation. And what tool do we use for this? We will also use a Maxwell model. So in the Maxwell model, again, we will have a total strain rate, and there will be contributions of individual mechanisms. So here we will have a viscous mechanism and an elastic mechanism. So we assume that the rocks can deform both elastically and viscously at the same time, and we do a serial decomposition, a Maxwell decomposition. So that's how we can represent this. The spring will be a symbol for the elastic element, and the damper is a symbol for the viscous element. This is a serial assembly of two rheological elements. Each of them have their own strain rate, but the whole chain is feeling a single stress. There's one stress value. So let's express this Maxwell model for viscoelasticity, and we will start by going back to expressing the stress in an elastic medium. So in an elastic medium, the deviatoric stress is proportional to the strain, not to the strain rate. So here you notice tau stands for the deviatoric stress, and epsilon is the deviatoric strain, the elastic part of it. In that case, the relationship is made with the shear modulus, G, which is a coefficient of unit Pascal. So we can solve for the elastic deviatoric strain, and this is tau divided by 2G. But what we need in this relationship is not the strain, but the rate of the strain. So let's take the rate of the strain. The dot is appearing here. The time derivative is here of tau divided by 2G. We now make the assumption that G is constant, so it gets out of the derivative, and the dot is only living on top of tau. So let's now take part of the viscous, take care of the viscous part of the chain. Let's write up the proportionality of stress and strain rate for the viscous medium. So tau is equal to 2 eta times epsilon dot. This is the strain rate here, the viscous part of the strain rate. So we can solve easily for the viscous part of the strain rate. Let's do it. Epsilon dot viscous, the deviatoric strain rate, is equal tau divided by 2 eta. So we have two strain rates that we express, so we can construct our viscoelastic Maxwell model. That's the chain here. Epsilon dot, the total strain rate, is equal tau dot, the deviatoric stress rate, divided by 2G, plus tau divided by 2 eta. The Maxwell viscoelastic model is here an ordinary differential equation, because in the same equation you have the rate of the stress and the actual value of the stress. We have two material parameters, the viscosity in Pascal times seconds and G in Pascal. So what's the unit of the ratio eta divided by G? Pascal times seconds divided by Pascal gives you unit of time. And this is the characteristic Maxwell time for a viscoelastic medium. So you have T is equal eta divided by G. The interpretation is that it's the time needed to reach 63% of the viscous flow stress when starting a build-up from zero. But this we will see graphically. So it is a characteristic time that represents the viscoelastic stress buildup. So let's start with a simple diagram. We aim at representing the stress evolution as a function of time. If we take the viscous element, the stress is simply 2 times eta times strain rate. We assume the strain rate is constant with time. So if you have the viscosity, which is also constant, tau will be constant with time. This is the viscous flow stress. It does not change with time. Then we focus on the elastic part. The elastic part, we have tau equal to g times strain, elastic strain. The strain will increase with time as deformation is being applied. So the stress will increase with the strain. So in this diagram, you will have a straight line with a positive slope. And you see that these two lines will at some point intersect. So stress increases with time for the elastic counterpart. If we assemble the chain with the elastic and viscous element, we will have this response. So the stress will be initially following the elastic trend, and it departs from it in a nonlinear fashion and goes to reach the viscous flow stress. The Maxwell time will be the time for a given percentage of this loading. For those who've studied a bit of electronics, it is very similar to the charge of a capacitor. So this is the diagram for the charge of a capacitor. You see the voltage here reaching from 0% to 100%. It is charging in a nonlinear fashion, and it has a characteristic time for charging and discharge also. So that's an analogy between viscoelasticity and electronics. So let's go back to this ordinary differential equation, the Maxwell viscoelastic model. We can integrate it to obtain an analytical solution. So let's do it together. What we're going to do first, we're going to take the stress time derivative and isolate it on the left-hand side. So we put tau to the left-hand side, and we end up with this relation here, with stress here and strain rate here. Now we express the stress rate. It's nothing else than the time derivative of stress, d tau dt. Next, we divide the left-hand side by the right-hand side. So this results in 1 on the right-hand side, and everything which was there ends up here in the denominator. The next step is called separation of the time derivative. So we add d tau dt, and we multiply the right-hand side by dt. So dt is sitting here, and we have this expression on the left-hand side. Now it's time to integrate this equation. So we will integrate both sides. The right-hand side is easy, so we want to integrate dt as a function of time. So this will lead to t plus a constant. For the left-hand side, there's a bit more algebra to be done, but basically one can identify that the integral of d tau, or the primitive of d tau divided by this factor that includes tau here, can be formulated as a log function. So that's the natural log. So we end up with this expression. We can exponentiate the expression with the log. So if you take the exponentiate this expression, the natural log will disappear, but we will have the exponential of g divided by eta times t with the minus sign, or that side of the equation. We split the right-hand side. So you can formulate exponential minus g delta t times exponential of the constant 1. Let's rename exponential of constant 1. We just call it constant 2. So we now have 2g strain rate minus g eta times tau is equal to exponential minus gt divided by eta times the constant. So we have a general solution here for the stress as a function of time and material parameters, and also applied strain rate. What we're missing now is we need to make this solution specific. We have a constant here in the middle, so let's use an initial condition to solve for the constant. So let's do it. We will assume that the stress is 0 for t is equal to 0. So we set tau equals 0 and time equals 0. We end up with this expression: 2 eta strain rate minus constant eta divided by g. This leads to the fact, or to the expression, constant is equal to g times strain rate. So you can use this expression and substitute it in the general solution, and the expression will simplify to this. So tau is equal to 2 eta strain rate times 1 minus exponential minus g divided by eta times time. That's the solution that will allow you to predict stress buildup and stress viscoelastic stress relaxation. This you will use in exercise number 2. So composite creep is very useful. It's mostly based on Maxwell model. Alternative models can be used, but in the context of this lecture, we only use the Maxwell model to combine the different deformation mechanisms. So they can be used to, for example, build deformation maps to account for dislocation mechanism, diffusion mechanisms, and other mechanisms. So by using the Maxwell model, we keep in mind that each of these elements, rheological elements, they have a different strain rate, but they feel the same stress. The same principle can be used to combine viscous and elastic deformation, and in this case we can build a model that captures both the elastic and the viscous deformation mode, and everything which is between these end members are viscoelastic processes. So it's a very powerful tool. Maxwell model is a powerful tool because it allows us to do all these things, to account for the complexity of creep mechanisms, but also to account for elastic and viscous effects in the frame of a single model. So thanks a lot for your attention.